Last time I introduced first pre-bundles and then bundles. So let's recall how this was defined. So we fix a category, something which I called a C-infinity suitable category, which means that all our objects are manifolds, our morphisms are smooth maps, and all morphisms are isomorphisms. So this was the definition. And then a pre-bundle on a manifold M was given as a map that associates to each point of the manifold an object of our category. And this object was supposed to be isomorphic to some fixed object called the model fiber F. Like this. Isomorphic in the category. And so that's it's a very simple concept. And then we introduced local trivializations. And I defined what it means that two local trivializations are in C-infinity compatible, similar to the concept of C-infinity compatible charts, manifolds. And then we talked about an atlas. So if we are able to cover our manifold by mutually C-infinity compatible local trivializations, we call this an atlas of the bundle, of the pre-bundle. And now a bundle is a pair consisting of a pre-bundle and a maximal atlas. Similarly to manifolds, where a differentiable manifold is a pair of a topological manifold with a maximal smooth atlas. Okay, and then we also saw that once we are given a bundle, there are various ways to construct new bundles out of the given ones. Like, for example, you can pre-compose with a smooth map. Then the resulting bundle will be called the pullback bundle, or you can post-compose with a smooth functor. And then these functors are very often algebraic operations, like taking the dual vector space, or like taking the direct sum of vector spaces, etc. And this is another way to get a new bundle over the same manifold, but with different targets, right? So when we do the pullback, then the fibers here, these things stay the same. And when we do this push forward along a smooth functor, then the base manifold stays the same and the fibers change. All right, so one more notation in this context. So if we have such a bundle with a model fiber F in category C, then this group of isomorphisms on the model fiber, so that's a set of isomorphisms in my category, and it contains the identity element, because the identity is an isomorphism. It also contains any two compositions of isomorphism, and the inverse of an isomorphism is also an isomorphism. So it's a group. The thing is a group. All right. In a category, you have associativity of the composition. So that is a group, and this group is called the structure group of the bundle. So this is called the structure group of my bundle F. Okay, and now let's list a few examples of different types of bundles corresponding to different choices of category. And I will make a table here and write down the traditional name of the particular type of bundle that corresponds to this category C. Okay, so maybe to specify, let's say, here are the objects of the category, here are the morphisms between two objects, and here's the structure group. And here's the traditional name for the corresponding bundle. Okay, so let's start with, so this has always to be a C infinity suitable category. So let's start with the canonical one, maybe differentiable manifolds itself. So in differentiable manifolds, well, not all morphisms are isomorphisms, so this category has as its morphisms arbitrary smooth maps. So let's go over to the category where we only have morphisms and throw out all non-isomorphisms. So now I have a category whose objects are differentiable manifolds and whose morphisms are diffeomorphisms. And okay, so differentiable manifolds are the objects, and diffeomorphisms are the morphisms. And now if I have a model fiber, maybe I should also list the model fiber at some point. Model fiber, structure group, and the traditional name. Okay, so the model fiber could now be any manifold, right? So some differentiable manifold. Let me call it F. Now what's the structure group? The structure group is the set of isomorphisms of the model fiber. So that means it's the set of diffeomorphisms of F, right? The diffeomorphism group of my manifold F. In this case, it's an infinite dimensional group. And the traditional name of such a C bundle is just fiber bundle. So such a bundle would be called fiber bundle over the manifold M with fiber F. Okay, then the next thing would be vector spaces. Let's say real vector spaces of dimension n. So here the objects are n-dimensional R vector spaces. And the morphisms in this category would be all linear maps. But since we want to have only isomorphisms, I'm taking so linear isomorphisms here, restricted to those. Now the model fiber in this case would be Rn. I could pick any n-dimensional real vector space, so let me just pick the most canonical one, Rn. And now what is the structure group? The structure group consists of all isomorphisms from Rn to Rn, so linear isomorphisms. So that would be the group GLN. In this case, and such a thing is called an n-dimensional, is called a real vector space bundle of rank n. And in fact, usually one is too lazy to say vector space bundle, although this would be the correct terminology, but somehow people drop the space and just call it vector bundles, which is imprecise because we are not bundling vectors, we are bundling vector spaces really, right? Okay, so that is this. Then we can do the same thing over the complex numbers. Then we have n-dimensional complex vector spaces. So these are R linear, now we have C linear isomorphisms. Canonical model fiber could be Cn. And now the isomorphisms in this category of my model fiber would be all n by n matrices with complex entries which are invertible. And such a thing is then called a complex vector space, the vector bundle of rank n. Okay, well, there are more options. So for instance, we could look at the category Euclid. look like Euclidean n. In this case, the objects are n-dimensional Euclidean vector spaces. So it's an n-dimensional real vector space equipped with a scalar product. That's a Euclidean vector space. And the morphisms would then be linear isometries. So which are isomorphisms which also respect the scalar product. And as our model fiber, we could take Rn equipped with the standard Euclidean scalar product. Write it like this. So standard Euclidean product. That's the standard Euclidean vector space, if you like. So what's the structure group in this case? It's ON, right? It's a subgroup of GLN which preserves this scalar product, so that's ON indeed. And such a thing is then called the Riemannian vector bundle of rank n. Right, in this case, the fibers are Euclidean vector spaces, so that means we have on each vector space, we have additionally to the vector space structure, we have the scalar product. And this is, for example, what you do when you do look at Riemannian manifolds, then you equip the tangent bundle with such a Riemannian structure. So you look at it as a vector bundle of this type. Okay, good. Other choices? Let's say we take ORVECT n, which stands for, so in this case the objects are n-dimensional oriented real vector spaces. And the isomorphisms are then, or morphisms, they are now orientation preserving linear isomorphisms. So orientation preserving linear, R-linear isomorphisms. And again, as my model fiber, I can take Rn together with its canonical orientation, for which the standard basis is positively oriented. Standard orientation. Okay. So what is the structure group? Well, it doesn't have a very good name, really. So we have to look at all those matrices in GLN which are orientation preserving. It's called GL plus N. So these are all those n by n matrices with positive determinant. Yes, and that thing is then an oriented real vector bundle. What else? Well, we might combine the last two. N. In this case, we have n-dimensional oriented Euclidean vector space. Now we have both. We have now we have both. We have a scalar product and an orientation, and the morphisms should preserve them. So they are orientation preserving R-linear isometries. And well, Our model fiber would be Rn with standard Euclidean product and standard orientation. Now what's the structure? Now go SON. So this is an oriented Riemannian vector bundle. Good. What else? We could have a complex version, Herm n. In this case, the objects are n-dimensional Hermitian vector spaces. And my isomorphisms then have to preserve this, so this will be C-linear isometries. My model fiber would be Cn together with the standard scalar product or Hermitian product. What's the group? The unitary group. So this is a Hermitian vector bundle of rank n. So this is always of rank n. N has nothing to do with the dimension of the manifold in general. Right? So Hermitian vector bundle of rank n. Anything else? Yes, there's one more example. Namely, if we take our simply transitive G manifolds, G manifolds, G is a Lie group, we give a Lie group, and so the objects are simply transitive G manifolds. So remember, this means we have a manifold and the group acts on the manifold in a smooth manner, simply transitively. We discussed this last time. The orientation preserving, the morphisms in this category are now diffeomorphisms which commute with the G action. So G calls this G equivariant diffeomorphisms. What's the structure? First the model fiber. Well, as a model fiber, I just take the Lie group. Right, I can act on the Lie group by itself by right multiplication, and that is simply transitive, so that certainly is a long choice. But now what's the structure? So what is the structure? So what we would have to look at all G equivariant morphisms or diffeomorphisms from G to G. Diffeomorphisms, not group homomorphisms or anything. Just G equivariant diffeomorphisms from G to G. And it turns out that the resulting group is canonically isomorphic to G. This will be an exercise on the next exercise sheet. And the corresponding bundles that one gets with this choice of category are called G principal bundles. Okay, so this is quite a nice table of examples already. So these are more or less all the bundles that we will ever need. And they are all now done in one go. Questions about this? Not right now. Good. All right. So the next thing is to talk about sections of bundles. Bundles have been invented because one needs their sections, not because of themselves somehow. And so let me discuss sections. So the first definition, this first definition can be done on the level of pre-bundles. So let F bullet be a C pre-bundle on manifold M with model fiber F. Yeah, well, if I look at all these objects Fx that I get when applying this thing to the points of my manifold, and I take the disjoint union of those, of the manifold, then I call the resulting thing E. This is called the total space of the bundle. So then, this is called total space of my bundle. Note that these objects Fx, they are always sets because they are in particular manifolds, right? So they are sets. So we are really here talking about a disjoint union of sets. If this were C were allowed to be an arbitrary category, of course we wouldn't know what this disjoint union would be. But since they are sets, we can take this disjoint union as sets, and then the result is called the total space. And the canonical map from the total space to the manifold M, the map pi on the total space to the manifold M, that sends all elements in Fx to the corresponding point x with pi of Fx being x for all x. It's called the projection of the bundle. Or the pre-bundle in this case. Alright. And now I can tell you what sections are. So a section of this bundle, pre-bundle. So this is a map in the opposite direction. So this goes, let me call it S like section. This goes from M to the total space, such that S of X is such that if I go from M to the total space and then with pi I go back to M, I do this composition, and this is the identity of M. Or in other words, what this means is that the value of S of X always is in the corresponding Fx. Right, so this is contained in Fx for all x. So that's another way of formulating this. Alright, good. So this is a section. And for many of the classical bundles, sections have classical traditional names. So let's look at examples. And I'd like to make a table. So I have so M is a manifold, n-dimensional manifold, let's say. Differentiable manifold. And yeah, then let's make a table. So we have a certain bundle over M. Let's recall the model fiber. And then the traditional name for its sections. Okay, let's start with the simplest thing one could have, namely the trivial bundle. Where all the Fx's are the same. Now this could be anything, so let's take as our model fiber R, so all the Fx's are just R, So that means, what does a section do? Well, it associates to any point of the manifold an element in R. So this is just a real valued function. Or sometimes it is physicists in particular like to call these scalar fields. So, I mentioned this too. Functions, scalar fields. All right, and then we have the tangent bundle. Here the model fiber is Rn, and its sections are called vector fields. Now, scalar fields, vector fields, but it's not, I mean, somehow this convention is not good because it's not some vectors, it's particular vectors, namely tangent vectors. So one should actually call it tangent vector field. If we go to the dual bundle of this, right, this was one of the examples from last time where we applied a smooth functor to a bundle, and this smooth functor was the dualization functor applied to the tangent bundle. And then the model fiber is the dual space of Rn, which I could identify with Rn again if I wanted. The sections in this are one forms. And then we can apply further functors to this, like the exterior product functor. Model fiber is then the corresponding exterior product of Rn star. And these the sections in this one are called K forms. So this are the differential form bundles. Or we could apply, let's say, a tensor product power to our tangent bundle. So I take the P tensor power of the tangent bundle. I could also do the same thing with the cotangent bundle. Q's tensor power of the cotangent bundle, and I can tensor those together. And then we have the corresponding fiber here, so tensor power P of Rn, tensor Q's tensor power of Rn star. And in this case, the sections are called tensor fields of type PQ. So those are more or less maybe the ones we know from our differential geometry courses. All right, and now what I would like to do is, I would like to be able to say that a section is continuous or is smooth. And at the moment I can't do that because I map, what is a section? A section is a map from the base manifold, so that carries a topology to the total space. This does not carry topology. This was just defined as this disjoint union of fx's. This is just a set so far, right? And I would like to turn this E into a manifold in a canonical manner, because then I know what it means that a section is smooth or continuous. So this will be the next step. So that's what we want to do today. And in fact, for this concept of sections, we would be fine with pre-bundles. I also should say sections of pre-bundles always exist unless the fiber is empty, which is not an interesting case to study. I'm going to make this remark here. Remark. Unless F is the empty set, sections exist. Because then all the fx's are non-empty and I just associate any element to x. Now you have to say something. By the axiom of choice. And later when we talk about smooth and continuous sections, this will in general no longer be true. It It will be true for vector bundles, but not for principal bundles. All right. So how can I turn my total space of a bundle into a manifold? And here I want to use what we did in the very beginning of the lecture course when I told you how to turn sets into manifolds. I will go and write down the candidates for the charts and then have to check certain conditions. And then I know from this theorem that we had in the beginning that there's a unique topology and structure of differentiable manifolds turning these candidates into true charts. That's what we are going to do. All right, so how can we come up with charts for our total space? Okay, so let's. So what's the setup now? Now I need to look to take a true bundle. So let F be a C bundle on M with model fiber F. So let's say the dimension of M will be N and the dimension of F will be M. So dimension here to N, dimension is also manifold, right? The dimension of the fiber is N. All right, so what do I have? M is a manifold, F is a manifold. So I do have charts for M and F. But I also have these local trivializations of my bundle. And so what I will take a chart for M, I will take a chart for F, and I will take a local trivialization, and out of these three objects, I will construct a candidate for a chart of the total space. Okay? So, all right. So let's talk. Let the following be given. First, a chart, smooth chart. Well, at the moment doesn't matter if it's smooth or not. Chart Y for my manifold M. So that is such a homeomorphism of an open subset of M to an open subset of Rn. So U, call this Y and Vy. So U, Y is sitting in M. And Vy is sitting in Rn, n is the dimension of the manifold. So that is a chart for M. Furthermore, let's fix a chart of the fiber. So the second piece I need, I call this Z. So this is UZ, VZ. UZ is a subset of F, and VZ is a subset of Rn. So that's a chart of model fiber F. And finally, I need a local trivialization of my bundle. So local trivialization. And so this was denoted as phi dot. So this associates to any point in a certain open subset of my manifold, so a local trivialization. And let me call this subset U phi. Associates to this V phi x, which is an isomorphism of the corresponding fiber and the model fiber. Right? So that's a local trivialization. And defined on U phi. So Uy, Uz, and U phi, these are open subsets of the manifold M. Uy and U phi are open subsets of the manifold M, and Uz is an open subset of the manifold F. All right, and now I want to write down a candidate for a chart of the total space. So, and for this, I need a subset of the total space on which it is defined. I need a subset of some R to the something, and I need a bijective map between the two. So let's do that. So we put U, which, or to be more precise because it depends on this data, u of y, z, phi. So this is defined as the set. So let me take the union over all points in uy, and also they have also the b intersect, also the b in u phi. Remember uy and u phi, these are both subsets of M. I can take their intersection, I look at all points in this intersection, and then I take my trivialization. I have an open subset uz in the model fiber also. The phi phi's end up in the model fiber, so I can take the inverse of this uz. This gives me then a subset in fx, or fp rather, fp. Right? And I take the union of all those. And so this is a subset of E. It's a union of certain subsets of the FPs, where P runs through this subset of N. So that is the set on which my chart is going to be defined. So the target set in Euclidean space is V, also depending on these given data. And this is defined to be, well, I take uy intersect u phi, which is a subset of M, and I apply the chart y to it. I can do that because it's a subset of uy. So this gives me now a subset in Rn. M is n-dimensional. So this is a subset of Rn. In fact, it's an open subset because y is a homeomorphism and these are open sets. So it's an open subset. And I cross this with the uz, which is an open subset of the model fiber, and well, apply the z to it, then I land in vz, which is an open subset of Rn. So this gives me a subset of Rn cross Rn, which I identify with Rn plus n. And you see, this is open in Rn, this is open in Rn, so we definitely get an open subset in Rn plus n. So let's already note this at this point. This is the open subset. Okay. And now I need the bijective map between u and v. X, which also depends on the given data, from u to v. And it's defined as follows. An element in this set U is mapped to, well, I have to map something in the Rn component and something in the Rm component. In the Rn component, what I do is I apply this projection map to it, so which gives me the foot point, sort of. It tells me in which fx the thing is sitting. So that's an element in the manifold M. And since by this definition, the only values that I can get from this are the ones which are in the intersection of uy and u phi. Right, so this is where I land. So in particular, I'm landing in uy, so I can apply my chart y to it. And then I get something in vy, and I get something anyway, I get something in the image of y of this intersection. So that's okay. And the other component, the component in the vz part, this is as follows. I take this element, and so that is an element in the fiber, in F with the foot point pi of E, but I want to get in the model fiber because this is where I have my chart. So let's apply the local trivialization to it with this base point. then I obtain an element in F. And in fact, I have arranged this in such a way that I'm guaranteed to land in UZ. So I can apply my chart Z to it. And then I land in BZ. Okay. So that's the map. Now, this is the construction. Now, we need to know that these maps X are bijective between U and V. And in fact, I can give you the inverse of this map directly. So X is bijective with inverse map X to the -1. Now I have to tell you what I get if I insert a vector from Rn and a vector from Rm into it. And what we get is, so I first apply the inverse chart to W, then I land in the model fiber, and then I apply the inverse of the local generalization with the corresponding base point here, so which is y to the -1 of V. So this lands me in M, right? And I apply this, and that's it. And then you can check that these two maps are inverse to one another. So what I have is now, starting from these data on M, F, and the bundle, I construct these new data, which are a subset of the total space, a subset of Rn plus M, and the bijective map between them. And now I want to check the conditions of the theorem that we had in the beginning of the lecture course, which will then guarantee us that this total space carries a unique topology and a unique differentiable structure such that these things become charts, smooth charts. All right, so let's do that. So then we have to remember what the conditions are that we had to check. In fact, if you remember, we had two collections, in fact, of such bijective maps. One collection and a countable sub-collection. And this countability had to do with the fact that we wanted to prove that the basis of the topology that we are constructing has a countable base. And so this is why I need some remark. So let me, or some notation, let's say. So let denote the differentiable structure of M by AM. So it's a maximal C infinity atlas on M, right? And the one on the model fiber by AF. And the maximal C infinity atlas of the bundle. So denote the maximal C infinity atlas of local trivializations of my bundle F bullet by A F bullet. So these are the sets from which Y, Z, and Phi are coming. Now, of course, these are uncountable sets, right? And I want to get countable subsets for those. Now, there's one remark. Since manifolds are manifolds M and F, since they are manifolds, and by definition manifolds do have countable bases, we know they do have countable bases. And if you know that you have a countable base on the top of a topological space, then each open cover has a countable subcover. Needs to be proven, is not hard, but you have to check that. So in particular, if I take all charts on M coming from this differentiable structure, then the chart domains cover M. And then I know that I can select a countable subset of AM which still covers. Right? Okay, so since manifolds, since the topology of a manifold has, by definition, has a countable base, we can take the atlas of M, for instance, and select a countable subset of it, so that the chart domains still cover all of the manifold. So that means I have a sub-atlas consisting only of countably many charts. So there exist countable sub-atlases A at 1M, A of M, similarly A1F of A of F, and also for this atlas by local torizations, so same thing, right? So the domains of these local torizations cover my manifold. I just select a countable subset which still covers, and then I get a countable sub-atlas here too. Same reason. Okay, and now I put A to be AM cross AF cross A F bullet and A1. This is not A and A1. I do the same thing with the countable versions. Right, and then A1. So this Cartesian product of countable sets is again countable. So A1 is a countable subset of A. So this is exactly the notation from the theorem from the beginning of the lecture. We had an index set for our charts, A, and a countable subset for that. But we have to be careful. The role of the manifold M in the theorem at that time is now being played by the total space E, not by the base manifold M. The base manifold is already a manifold, so there's nothing to worry about that. All right, good. So we have that, and now I want to, now to each element in here, chart here, local torization here, I have associated a candidate which should still be on the board, given of the set U, the set V, and this bijective map between them. And so I have all the necessary data in to check to apply the theorem, except that I have to check these conditions. And so, what are the conditions? So we have to remember the conditions. The conditions say that if I take this countable subset, then this still has to cover my whole manifold, which in this case is the set E, the total space. So the U's coming from all these elements in A1 need to cover the whole total space. That's the first thing. The second thing will be to check if I intersect two such U's coming from two different triples, and I apply the chart of one of them, then I get a subset in Rn plus M, and then I have to check that this is an open subset. That was the second thing to check. The third thing was to check that if I do coordinate transformations, so if I compose one of the x's with another x inverse, then I get a diffeomorphism. That's the third thing. And the final thing to check was to say that if I have two elements in total space in this case, then I can find a chart coming from an element in A that contains them both. Right? These were the conditions. And then if we can check this for our candidates of charts, then we know we can turn them into charts by giving a unique topology to the total space and unique differential structure. All right, so let's start with number 1. So we have to check that these sets U, when I let y, z, and phi run through all elements in A1, so that they cover the whole manifold E, or whole space E, total space E. Okay, so let's see. Let's start with an arbitrary element in E. And let's see that it is contained in one of these chart domains for one triple coming from A1. Okay. All right, so then first thing is we choose a chart Y in A1 containing the image under the projection. So such that the image of the projection, which is an element in the base manifold M, and every point in the base manifold M is contained in some chart, because this is an atlas. Right? Good. Next, we can also choose a local trivialization phi in A1 of the bundle, so a local trivialization of the bundle, which is defined on this point, because the domains of these local trivializations also cover the manifold M. Trivialization such that pi of E is contained in its domain. Good. Once we have that, we can use this local trivialization to map the point E itself to the model fiber. Right? And then we are landing in the model fiber, and then we pick a chart that of the model fiber which contains this image point. So choose chart Z in A1 of F, model fiber, such that the point obtained by applying the local trivialization to E, which is an element in F, is contained in the corresponding chart domain. All right, good. And well, then let's look at the definition of our U here. The definition was like this. So in particular, if I look at the case, if I look at P equals pi of E here, which is admissible because pi of E is in Uy and in U phi. This is how we chose Y and phi. So I can look at this for P equals pi of E. Then I see, okay, I can take any point which, when I map it back with the local trivialization, land in UZ. But the UZ, sorry, land in UZ. Land in UZ, and so the E so the image of E satisfies this. So the E itself lies in the pre-image of this. And so this means that the E itself lies in this set U. This is how I set it up. So then E is an element of U, Y, Z, phi. And this shows that if I take the union over all alpha in A1 of N in A1 and look at the corresponding U alphas, then this will cover all of E. I mean, all U alphas are subsets of E, but I've shown that any element is also contained in one of them, and so the union is all of them. That was the first condition. All right, so now the next one is to check the intersection of two such U's for two different triples, map them with one chart to Rn plus m, and then check that the result is an open subset. We're going to keep the definitions here, and just erase this part. We certainly can remember this, right? So, second condition. So let's start with two such triples, so that alpha consisting of y, z, phi, and beta consisted of y tilde, z tilde, and phi tilde, in two such triples. Okay. Then I have the corresponding u's, v's, and x's. And so let's see what I can say about the intersection. So let's say, so u alpha intersect u beta, what is it? And here's the definition. So I have to take a union. So the first ones are the ones where P runs through. This I can just copy, right? So this is uy intersecting phi. Of all the phi P minus ones z. So that is alpha. And this is to be intersected with the union of all P in u tilde intersect u phi tilde of the corresponding phi tilde P to the minus ones z tilde. Okay? So in other words, I take the union, so the admissible P's here are only the ones coming from the fourfold intersection of these four sets. So let me rewrite this as the union of all sets uy intersect uy tilde intersect u phi intersect u phi tilde. And then I have elements contained in this one and at the same time this one. Okay. That's what I have. So, but I'm not interested in this set, in the intersection of this itself, because this is a subset of E. I want to apply the chart X alpha to it, then I get a subset of Rn plus m, and I want to check whether this is open. So that means that V, so this is what I'm really interested in. X alpha of U alpha intersect U beta. So let me try to characterize the points in this set. So V comma W, so this V again is the Rn part, the W is the Rn part, subset in Rn plus m. So when is V comma W of in this set? Well, of course this is if and only if x alpha to the minus 1 of VW is in the set that I've written down here. And I had a simple formula for the inverse of such a chart map, which should still be here somewhere. It's this one. So let me copy that one. So this would be y to minus 1 of y to minus v applied to z to the minus 1 of w. Okay, that's the condition. And this is if and only if. Now let's take a look at the set. So I have to take, so first of all, this point here, this y to the minus 1 of v, must be an element of this fourfold intersection. So that's the first condition. That's my p then. And what about the z to the minus 1 of w? Well, z to the minus 1 of w must be in phi, y to the 1 of v, applied to this set. But this map is just the inverse of that map. So what I get is the condition that I have something in uz intersect, and here I have phi y to the minus 1 of v applied to phi tilde inverse y to the minus 1 of v applied to this set uz tilde. So these are the conditions. All right. Okay, so let me take this the set on the right hand side and give it a name. W is this fourfold intersection, so that's a subset of my base manifold M. Subset of my base manifold M cross, and this other thing is a subset of the model fiber F, right? So cross uz intersect, and here I have the transition map between the two local trivializations. Applied to uz tilde. So let me give this name. So the condition with this terminology, right? The condition that v, w is in the set that I'm interested in is to say that the element y to the minus 1 of v, comma z to the minus 1 of w is contained in this set category. Okay, well, so the first thing is not terribly bad, right? So this is an intersection of open subsets of the base manifold M. So it's definitely an open subset of the base manifold M. It's contained in Uy, so the chart map Y is defined on it. And yes. And this other thing looks more complicated because it also depends, so this concerns the second variable W, but the condition also depends on V, not just on W. Good, but that's not a problem, namely, this W is the pre-image of the following set, an open set. So this fourfold intersection, Uy intersect and so on up to U phi tilde, cross, and then I have uz tilde here under the smooth and hence continuous map. So the map is going from Uy cross uz and Uy cross uz to Uy cross uz tilde, and is mapping P Q to P, and here we have the transition phi tilde P minus 1 composed with phi P applied to Q. So, and so that this map, so this just encodes the fact that this that a point is in this map W. And the point here is that the transition between two local trivialization was defined to be smooth in both variables Q and also in this good point P. So the second component is a smooth map, and the first component is just a projection on the p part. It's also smooth. So this is a smooth map from this set to that set. And if you check that, if you look at the pre-image of this subset in here, then you get the W. But this means, since this is an open subset, it's a pre-image under a continuous map. This means that the W is an open subset of M cross F, right? Need this anymore? Therefore, W open in M cross F. Now, Y and Z are homeomorphisms. In fact, it's contained in UY cross UZ, which in turn is contained in M cross F. This is an open subset in here, and W is open in here or here, doesn't matter, makes no difference. Okay, and now Y, Z, these are the two charts, so they are homeomorphisms onto their images. Y, Z from UY cross UZ to VY cross VZ is a homomorphism, which tells me that these points, the pairs V, W themselves, form an open subset set. These pairs, and that's exactly the set of which I'm considering here. So X alpha of this intersection is open in Vy cross Vz. Right? Because it's a map on an open set under a homeomorphism, so we get an open set in here, but that is open in Rn plus M. And therefore, it's also, this subset is also open in Rn plus M. Because this set is open in Rn plus M. And this one is open in this one. Okay, so that is condition number 2. That was the hardest one. Not really hard, but you just have to unravel the definitions. Yeah, all right, that's true. So what I mean I should write the union where V runs through this set. Yeah. The question was, what does the definition of W make sense? Because here it seems to depend on a point, which we haven't chosen, so we have to run through all the definition is still there somewhere. So maybe I just say I'll let it depend on V, okay? And then I would say, okay, this pair is contained in the set I'm interested in if and only if this is contained in that. And so on. Now, the transition maps. Number 3. So I have to look at X alpha composed with X beta to the -1 as a map from some subset of Rn plus n, in this case to Rn plus n. So let's apply it to VW. And I hope we still have the formula available. So first the inverse, we have it down there. So that would be X alpha of. And now I have to do this with the second chart where all the charts carry tildes. So what I have is I tilde to the -1 of Y tilde to the -1 of V applied to z tilde to the minus 1 of w. And then I have to apply x alpha to that. And all right, so what is it? So we have to do, what we have to do is, unfortunately I erased the definition of x alpha. It's still here, exactly. So the first component is obtained by looking at the projection and apply the chart y to it. So this is the base point, and I have to apply the chart y to it. So this gives me y of y tilde to the minus 1 of v. So that's the first component. And for the second component, I have to take z, apply it to phi of this base point. So p is given as y tilde to the minus 1 of v. And then apply that to the whole thing. So this is my E, right? So apply this to y tilde to the minus 1, apply it to z tilde to the minus 1 of w. Counted it right. Yes, this is correct. Okay, so that's it. So in other words, the first thing gives me just a transition map between two charts on the base manifold. That's good because we know that this is a diffeomorphism because we are looking at smooth charts of the base manifold. And then here what I have is Z composed, and here I have the transition map of these two local trivializations at the foot point y tilde to the minus 1 of v, composed z tilde to the minus 1, and this whole thing then applied to w. And now, okay, we need to check that this is a smooth map in terms of v and w. So the first part is, as I said, is easy. So that's a diffeomorphism applied to v. So that's certainly smooth. And the second part, this transition map, is smooth both in this argument and in the foot point argument. The foot point also depends smoothly on v because this is a smooth chart. And that is a smooth chart, so the whole thing also depends, this depends smoothly on w. So this depends smoothly on v, w, and then you apply a further smooth map, so that is also smooth. Right? So this is smooth. That's the third condition. And finally, for condition number 4, we have to check that if I have 2 points in our total space, then we can find the chart containing them both. Okay, so let E and E tilde be 2 elements in the total space. Case 1. Let's say the foot points, so if I apply the projection to them, these corresponding points in the manifold M, they could be the same, they could be equal or not equal. So let's first look at the case where these projections are also not equal. Okay. Then what I can do is, I can find a chart of the base manifold containing these 2 points. Choose a chart Y of the base manifold such that these 2 things are both contained in the corresponding Y. All right. Next, I need the trivialization. And I can also find the trivialization such that the corresponding domain contains them both, because these 2 points are different. So you can find one which contains this one, and you can find one which contains that one. You just make them very small so that they are disjoint. Right? The manifold M is Hausdorff. You restrict them to smaller neighborhoods of this one and that one, and then you take the union of these two sets. I never said that charts have to be connected. Okay, so choose local trivialization of the bundle such that there are 2 points here are contained in U phi. And now I check what the local trivialization does to these 2 points. They both map them to points in the model fiber, and those could be equal or unequal. But actually, maybe I don't need this assumption at this point, because I could do this no matter whether these are different or not, right? I mean, if they're equal, then I can do this in any case, then there's nothing to be worried about. I haven't used this condition yet. So now, but anyway, when I now apply my local trivialization to these 2 points, to E and E tilde, which I can do because of this. How should I say that? Choose the chart maybe I make it a picture. So okay. So this is the base manifold M. Here I have maybe E. I'm drawing the case where everything is different. So then I have pi of E here and pi of E tilde here. So this is the schematic picture, right? And now, of course, it could happen that these 2 are equal, then they lie on the same fiber. But in any case, that doesn't matter. So I now need a chart so if the 2 points pi of E and pi of E tilde coincide, then both these points lie on the same fx, and then so I want to go to the model fiber and then choose a chart there. So my local trivialization is defined for both of them, so it maps them maybe here, maybe here. Right. So I get the phi gives me 2 points on the model fiber, and I choose a chart now which contains these 2 points on the model fiber. Okay, so choose Z and A of F such that it contains so phi pi of E applied to E and phi pi of E tilde applied to E tilde are contained in the corresponding chart domain. And with this choice, then I have a set which contains both E and E tilde. Then E and E tilde are contained in the corresponding set U y, z. So it was not difficult, but I was just got a bit confused. All right, so these are the four conditions, and I've checked them, and so the theorem now gives me that, so we have proved that we can find a good topology of a total space. Okay, so we have shown the following theorem. There exists a unique topology on the total space E and differentiable structure such that the set of so that A given as the set the following triples x alpha from u alpha to v alpha, where alpha runs through A, and the same thing for A1. So these charts that we have constructed, x alpha from u alpha to v alpha, where alpha runs through A1, that these two are C infinity atlases of E. Okay, in particular now, we can speak about continuous and smooth sections. C0, C infinity sections. Or you could also talk about CK sections when K is 5 or something. This is all defined on smooth manifolds. Now sections are maps between smooth manifolds, and from manifold N to manifold E. Good. Can we characterize somehow the smoothness or continuity of such a section directly in terms of the local trivializations? In fact, we can. And the following are equivalent. A section S of the bundle F is smooth in the sense that it's a smooth map from M to E, or the maps given as so if I have any local trivialization, the maps which from U to F given as X is being mapped to take the section, then I'm landing in the fiber Fx, and then I want to apply a local trivialization to it, Fx. This is now a map, this now lands me in the model fiber. And these are manifolds from the start, because this is the open subset of the manifold M, and F is also a differentiable manifold. So we already knew what smoothness means in this case. These maps are smooth for all local trivializations in one smooth C infinity atlas. For all phi defined on U, mapping x to phi x in isomorphisms from fx to f in some C infinity atlas of local trivializations of f. So we can check the smoothness directly in terms of the local trivializations as maps from U to the model fiber, or the same statement holds for all these atlases, so for the maximum C infinity atlas, just for some. So so we have, if it's smooth, then this is smooth for the maximal atlas, so for every local trivialization, but it's sufficient to check it for one collection of local trivializations which cover the manifold. Yeah, that's an exercise to check that. It's similar to checking smoothness of maps between manifolds. You can do it, so it's equivalent to say it's smooth in all charts of the manifold or in one collection of charts which covers the manifold. Similarly here. And now you can compare this to the traditional definition of bundles. So the usual definition in the literature of bundles doesn't use this categorical language. Rather, they say, well, a bundle consists of a total space E, which is a manifold, and a projection map to the base to another manifold, which is called the base manifold. And then you have local trivializations, pretty much the way I described them. You can do that. So we are coming from the differentiable manifold setting to define this. But then if you have a vector bundle and you want to associate a functor to it, fiber-wise, then they say, well, if you have bundles on, then take the dual vector space for each fiber, and this gives you a new bundle. But then you lose the differentiable structure, the topology and everything, because you have to argue that if you do a fiber-wise construction to this, then a priori you do not have a differentiable structure or topology on its total space. So if you do it properly, you have to do it this way. So I wanted to do this once and for all. So this applying, also the pullback definition is a little bit more involved in this setting, in the traditional setting, because then you cannot just compose with the map. You have to write down the total space of the fiber product in terms of the pullback bundle in terms of the fiber product, etc. So I think this is the cleaner approach. And the nice thing is that it gives us all kinds of bundles at once. Good. So that's it for today. And then we are pretty much at the end of the general bundle theory. I will then say a little bit more about vector space bundles next time, because we will need connections in their curvature tensors. And once we have that, we will be able to talk about characteristic classes, provided we know the home of characteristic classes, which is the RAM cohomology. In the Moodle, you find an introduction to the RAM cohomology, which contains pretty much everything that we will need. So if we need anything, you can always look it up in these lecture notes. So they are pretty condensed and contain everything which is relevant to us. Okay? Good. So this is for today, and so thanks very much for the attention.